Good morning, evening, not sure when you're going to see this, but what I thought I would do is a short video that just summarizes the kinematic terms that you guys are going to be responsible for. Okay. I know it could be overwhelming, but it's just trying to keep it simple. Remember, that's why Physics 207 is a prerequisite for this, because with beginner physics, you should have at least introduced to these topics, and it's my job to apply them to biomechanics. How are we going to use this? We're doing for a living, right? So what I wanted to break down in my way, which I learned from my major professor, is how build upon each other. What I mean by that is this is made up of some of that, and this is made up of some of that, and this is made up of some of that. I think the analogy I try to use to cake. It's a lot of different things. So with our kinematic terms, I have a common symbol that you're going to see in equations or in books, and there's some variability there. But more importantly is the units, like that, and the units to me works well because that's when you can put it into perspective in context that you're familiar with. We're not really familiar with these symbols, but we're familiar with context of how this stuff applies to in our daily lives. Okay, so position, where are you at? And when I say you, it could literally be you, or it could just be the object you're talking about. If you're coaching football and the quarterback's throwing the ball, you may want to talk about the football or help them in their mechanics and use certain objects from their perspective. So baseball, golf ball, the bat, the ball, the whatever. Okay, where is that at? Whatever you're talking about. Remember in 310, we analyze motion joint by joint, kind of that kind of stuff. Well, we apply biomechanics object by object. Okay, so whatever object you're talking about, in this case, I'm going to use, an example of a sprinter athlete. Where are they at? And a symbol, but XYZ coordinate. But in real terms, it's, let's use a football field. Are you at the 10? Are you at the 20? Are you at the 30? Are you at midfield? That's coordinate system. You think about how the football field is laid out in coordinates. Basketball court is laid out in coordinates, kind of. The free throw line, half court line. It's all coordinates. Far court, near court. It's coordinatal stuff. So think about an athlete running a sprint. Where are they at to start? Well, wherever the starting line is, it's a designated location, place. So your position is going to be at that designated start. Where are you at? So at the start, they're going to be here. And then when the time stops, they're going to be over here. And what's cool is it doesn't matter where they go. They can run through the gate. They can run down Highway 14. It's where did time stop? That's the snapshot of start finish. That's what matters. So for a race, your change in position, where did you start? Where was your location when you started? And where was your location when you finished? That, and we call that a delta, a change. That's all delta is. It's just a change. That change in position is what we call distance or displacement. Now, what's the difference? Distance is as the crow flies. Distance doesn't matter direction, and displacement does. In football, we see this all the time. When a running back runs zigzag all over the place, it doesn't matter if they started left, come back around. They could have ran 50 yards, but they only get credit in a certain direction, right? Direction matters. You have to get 10 yards for a first down in a specific direction, okay? So for a 40-yard dash, if you run at an angle, you're wasting distance because you only get credit in a very specific direction, okay? So that's the difference. Distance is just how far did you go, and displacement is how far did you go in the X, in the Y, in the Z. How far did you go north? How far did you go east? How far did you go west? Okay, direction matters. So if someone is traveling northeast, they are separately displacing, let's say they go, their north displaces, and then their south displaces, or in this case, east displaces. I'm trying to keep up with myself. And then north displaces. So in other words, their distance is here, but how far did they go east and west versus how did they go north and south is a different, it's similar, but it's a separate thing that we need to look at when direction matters, okay? Distance versus displacement. Now, what's cool is, again, position, distance and displacement has position in it. It's made up of change in position. So this concept has some of this in it. Another way to look at distance or displacement is how much time did it take you to displace? How much time did it take you to distance? If all we did was talk about running with distance, you'd have a lot of ties. What I mean by that is if you had 100 people run the 40-yard dash and all they did was measure distance, unless you hurt yourself midway, everybody would distance the same. Everybody would displace the same. So how do you separate athletic achievement? You add an element of time. Time is scalar. There's no direction to it. Same as position. But time allows us to say, you displaced and I displaced in different amounts of time. So therefore, we have a new term that we can extract from that: speed. Speed is the distance term for how much time did it take you to distance. And velocity is the directional term for how much time did it take you to displace. How much time did it take you to go from A to B? How much time did it take you to go from start to finish? Now that we could start separating a lot of things, right? If someone displaced in less time, the smaller the time, the larger the velocity. And inherently, you know this. The 40-yard dash is a test of what? Speed. But yet we never talk about it in units of speed. No one ever says, how fast did you do in the 40-yard dash? And you say, man, I did really well. I averaged 22 miles an hour. You don't talk about it like that because you do the physics in your mind. We're all displacing the same when we run a 40. So smaller denominator time inherently makes a larger resultant once you plug in the numbers. In other words, for the equation of velocity, you have delta change in position in regard to time. So since this is the same for everybody, smaller this means larger that. So when someone says they ran a 40 in 4.3 as compared to 4.5, you understand that smaller numbers here mean larger velocities all around. But again, what's cool is that speed and velocity has displacement in it. It's right here. And it has position in it. It's all in there. It's all in the recipe for it. The concept of acceleration is that units of speed, let's go to your car, again, something you're very familiar with. And your car has miles per hour as a unit of speed. And I say speed because unless you have a fancy car that gives you direction, you're going north, northwest, but even then it doesn't extract how much of that speed is north, how much of that speed. We're going to get into that with trig. But the point is that you are extremely familiar with the concept of speed. Now, speed is any notch on that continuum. 0 miles an hour, 5 miles an hour, 10 miles an hour. That's a unit of displacement over time. If you're at 20 miles an hour, you are going to displace, you're going to distance 20 miles per unit time, per hour, okay? Where acceleration comes in is acceleration asks this very simple question. Nothing changes, just like up here, nothing changes position instantaneously. That would be like Harry Potter magic, right? Everything takes time to displace. It takes time to displace. The same logic falls with speed. It takes time to change your speed. Everything takes time to get faster or to get slower. So if you're at a stop sign, it takes time for you to go from 0 to whatever in speed you're at. It also takes time. Sorry, I'm moving a pop-up. It takes time to slow down. If you're cruising at 50 miles an hour and you come to a red light or a stop sign, it takes time. So the concept of acceleration is very simple. It is how much time did it take you to speed up or to slow down, to go from your initial speed to your final speed. How much time did that take? What was your initial? Was it 0? What was your final? Was it 60? Car dealerships infer acceleration all the time, just like we infer velocity. I ran the 40 in 4.3 seconds. I inferred my speed. Car dealerships infer acceleration all the time because we don't really kind of know what a good acceleration is, meters per second squared. So what they do is they use layman's terms, 0 to 60 in 4.2 seconds. That's what I have right here, 0 to 60 in 4.2 seconds. That's an inference of acceleration. How much time did it take you to change your velocity? Okay. Now, the cool thing about acceleration, changing velocity, so you can really keep it simple. Acceleration is just change in velocity because everything takes time to change velocity. So the time component is inferred, just like the speed component is inferred. Everything takes time. But the cool thing about acceleration is this is the term that links kinetics with kinematics. These are all kinematic terms and variables. Kinetics and kinematics is linked between acceleration because anything that changes velocity takes time, but it's because there was an outside force that was responsible for speeding it up or slowing it down. I cannot speed myself up, nor can I slow myself down. Something has to speed me up or slow me down. Even if you think about, well, Doc, I could jump up in the air. The ground got you up in the air and planet Earth brought you back down. If I laid down on the table and flailed my legs and arms, I ain't going anywhere. I can try to move the ground. The ground ain't going anywhere. The ground gives me force back, and the ground actually applies a force, thus accelerates me. Okay? So that's the key. We're working towards understanding that it's speeding up and slowing down of objects that require outside forces to do it. Anything that speeds up or slow down takes time, thus acceleration. Now, another thing too is that everything that speeds up and slows down is a type of acceleration. In biomechanics, there's no such thing as deceleration. F is equal to ma, not F is equal to ma, and sometimes F is equal to md. Acceleration is a vector quantity, thus it has direction, negatives and positives. So positive accelerations and negative accelerations. So you may say, well, Dr. Campbell, how do we say deceleration? You say slow down. If you want to infer that decelerate means slowing down, then just say slow down. But what we can't do is we can't infer that acceleration means to speed up, because by default that means deceleration must mean to slow down, and that's not true. Acceleration just means change in velocity, just like velocity means change in position. So acceleration does not necessarily mean to speed up. When you slam on the brakes, you're accelerating. Okay? So I hope this little summary video kind of helps bring some of this stuff together. I'll try to do this after all the subsequent lectures to get you guys ready for your test. All right? Hit me up if you guys need. Bye.